Okay, good morning. This morning I have to go to a Yukon meeting, so I may be in class for a little bit, but I have to do a virtual meeting for the Yukon certification. All the state teachers for ECE are doing this meeting, just happened to fall this week. So I just want to do a quick asynchronous. I'm going to post this video, watch the video, then attempt to do the homework. I think I'm going to assign the homework. So watch the video first, then do the homework. And follow the instructions on Google Classroom. So the big thing we were talking about is comparing, when the way we have you guys use Newton's laws are comparing how the forces add up. So if the forces are balanced, we know it's the first law, and that the sum of the forces left equal the sum of the forces right, and forces up equal forces down. Those are easy. It's the second law, which you guys did a lab on. It's a little bit more complicated, but not really much more complicated. So we like to teach you to think about, are the forces balanced or unbalanced? Is the object keeping on doing what it's doing, or is the object accelerating? So the second law looks at unbalanced forces. Another way of saying that is the net force. When you add up all the forces, they don't add up to zero. So there's a net force that's greater than zero. So the trick to this is trying to figure out what the overall forces are by using a free body diagram, and then trying to figure out what the net force is. Then you set that net force equal to MA, and that should allow you to calculate anything. So we need to find the net or overall force. And it's really just a comparison. It's kind of like a tug of war. So you draw the free body diagram, you compare the forces and see who wins and by how much and in what direction. So I want to do a couple of quick examples in your notes. And I apologize because my picture's down here in the corner, but you'll have to endure that. So I would suggest you get down a couple of examples in your notebook. And each example is going to get progressively a little bit more difficult, but they're still not that difficult. So we're going to start with example one. It says gravity pulls a skydiver downward with a force of 600 newtons, so that's sort of weight, 600 newtons pulling him down, but air resistance pushes back up, and that force is going to be 460. So in physics, what we normally do is we draw an object, and almost all objects, we just draw them as boxes or points. So I'm going to draw it as a box. So it doesn't matter what it is. It also doesn't matter where you apply the force. I generally say if the force is going down, put the arrow on the bottom. If the force is going up, put the arrow on the top. You could draw a vector pointing down on the top, but it's a little confusing if you do it that way. So I'm going to show this force going down, which is 600. That's the weight of the person, so that's FW equals 600. And then it says at the same time, air resistance pushes back upward with 460. So I'm going to draw that vector a little shorter. They don't have to be exactly scaled, but you should get in the habit of drawing them approximately correct. I'm going to call this friction. So I'll call it F sub F. And that equals 460. Eventually we'll learn how to calculate F sub F. But for now, we're just going to give you the value. So now I look at this and I say, well, are the forces balanced? And of course the answer is no. And so, like everything, we want to do it algebraically. So you can say F net. And again, I said this is kind of like a tug of war. We have weight pulling down, we have friction pulling up. Well, who wins and by how much? Well, and again, I know you can do it in your head mathematically, but I want the algebra. You'll see when the problems get much tougher, you want to be able to fall back on the algebraic method of doing it. So I'm going to say it's FW is the big one minus the little one, half that. It's always the big force minus the little force. So it's the guy who wins minus the guy who loses. So in this case, the net force, it's just going to be these two values added together. So I'm going to say F net added together vectorially. That would be 600 minus 460. And if I did my math correctly, the net force will then equal 140. And of course, we know from Newton's second law that equals MA. And so if I gave you the M or the A, we could solve for the other. Okay, so that's pretty simple. It's just compare the two forces, draw your free body diagram, get the vectors going in the correct directions, and scale them approximately correct. You don't have to grab a ruler. That will be the technique. Now, we're going to continue this with some other problems that get progressively more difficult. So now I'm going to have you draw a free body diagram, calculate the net force, but then we're going to then calculate the acceleration and look at what direction the person is accelerating in. So again, I'm going to do the same thing. Free body diagram. Well, here's an ice skater box. Pushes off with a force up. So she's going to push off. So let's assume she's going to go to the right. So I'm going to say this is the, now what I normally do in class is if somebody comes along and pushes something, I normally call it an applied force. So I'm going to do F sub A. We'll talk more about this later, but I have to give it a name. So I'm going to call it FA. You can call it F anything you want. So the applied force, I'm going to say 154 newtons forward. So I just arbitrarily pick to the right or east as forward. And then we say friction resists that force. So ice does have some friction. We're going to say it goes backwards the other direction. And again, I'm going to make it slightly shorter. I'm going to say the frictional force is 90 newtons the other direction. So again, as we did before, we have a free body diagram, we have it labeled, we have it scaled. And what I also do sometimes is I label the, let me change the thinness of my, I like to label the mass inside. We'll talk more about mass and weight later, but I like to put the mass inside the box. That way I don't confuse it with a weight. I'll talk more about that later. So I put 45 kilograms, that's the mass of the person. So now I want to calculate the net force. Well, again, F net is going to equal the winning force minus the losing force. So it's going to be the, well, which guy wins? Well, obviously the things that move forward, the bigger force is FA. So it's always going to be the winning force minus the losing force. And in this example, it's 154 minus 90. So that's going to be 64 newtons. Now, I said this before, along the way, you don't have to put the units. So at the end, you should put the units, but along the way, don't worry about it. Now, what I want to do is I want to use that 64 newtons to actually calculate the acceleration. So because it's the second law, I know the F net not only does it equal the big one minus the little one, but also equals ma. And so I can say the acceleration again, now equals F net divided by m. And it's going to be 64 divided by 45 on my calculator, but that doesn't sound 2. It's going to be 1 point something. I'll take 64 divided by 45, and I get an acceleration of 1.42. 1.42 meters per second squared. I guess that was a final answer. So there's newtons, circle it. Meters per second squared, put a ring on it, and it's positive. The thing can accelerate. So we apply two forces. We have an applied force, we have a frictional force. The frictional force loses, the applied force wins by a magnitude of 64 to the right. We can then use that with Newton's second law to calculate the acceleration. And of course, once we have the acceleration, we can do all the kinematics. The person started from rest, blah, blah, blah. So it can get much more complicated, and it is. So let's take a quick look at this one. Why don't you guys take a minute to do this one on your own? So it's a tug of war, Olivia 1, Olivia 2, and Jaden each pull on a rope with a force of 150 newtons east. And here's the rope. We've got Liv 1, Liv 2, and Jaden. And they're each pulling with 150. And then Wednesday and Autumn pull back with. So that's Wednesday and Autumn. Each pull with 253. Actually, I think I should show this one. So now I got three forces on the right, I got two forces to the left. And again, it didn't say what direction, but it's a tug of war, so we're assuming we're going opposite directions. Is this balanced or unbalanced? Is it the first law or the second law? Well, some quick math, I can say that's 450, that's going to be 5 something. So I definitely know it's unbalanced. It's the second law. These forces to the right don't cancel the forces to the left. So the sum of the forces left does not equal the sum of the forces right. And therefore, we have Newton's second law. Now, I can go out and get the net force. And to do this, I have to compare. Remember, it says the sum of the forces. We have to sum up all the forces pulling to the right. We have to sum up all the forces pulling to the left and see who wins. So what is the net force? Well, F net has to equal all the forces that are going to win. So who wins? It's the winning forces, which is Wednesday and Autumn. So it's going to be force Wednesday plus force Autumn. Parentheses, add those together. And then the big ones, minus the little ones. So it's going to be force Olivia 1 plus force Olivia 2 plus force of Jaden. So it's going to be we know this one's winning. We know that 250 or 506 is bigger than 450. And again, pick numbers you can do in your head. So it's going to be 253 plus 253 minus, was that 150 plus 150 plus 150. And I know this is a little tedious, but again, when the problems get more complicated, you'll want to see how this is done. But anyway, so I add this up, and I'm going to say, well, that's going to be 506 minus 450. So now I have the net force as being 56 newtons. And it's in the left direction. You could specify that as a negative, or you could say it's left. You could do it either way. I'll just say left, but you could say it's negative because it's in the negative direction. So what direction is the acceleration? Well, the acceleration is always in the direction of the net force. So if the net force is to the left, then the object's going to accelerate to the left. And again, we could then we could change some things. We could calculate the acceleration. For some reason, I had Olivia consuming tons of Skittles. Oh yeah, she eats lots of candy. Sorry, Olivia, I didn't specify which one, but you guys can fight over that. But Olivia eats lots of Skittles, and now she has much more strength. She can now pull at 350, calculate the new net force. Well, if one of the Olivias is pulling at 350 and the others are pulling at 150, then you can get the new net force. And again, you're just comparing the winning forces. The net force is always going to be the winning force minus the losing force. It's always going to be the sum of the winning forces minus the sum of the losing forces. And most of it's pretty intuitive. I mean, I'm making it really algebraic and all that, but most kids look at it and go, oh, that guy wins. The problem is sometimes we don't have numbers. I've said this before. UConn will often send a test where there are no numbers and you have to express it algebraically. So I want you to get in the habit of doing it that way. Now, the other thing I just want to mention here, and this is a little confusing when you first go through it, you guys have probably heard that weight and mass are not the same thing, and they're not the same thing. So the mass of an object is how much stuff you have in your body. So your mass is your stuff. So that doesn't change. If I go to China, my mass stays the same. If I go to the moon, my mass stays the same, assuming you don't eat food or cut off my arm or something. So if all the stuff in my body stays the same, approximately, then my mass will stay the same. But your weight changes based on where you are. And we'll look at this in more detail later when we study gravity. But for the time being, we're going to say the weight of an object is the amount of force. It's not a mass, it's a force that the object is pulled towards the Earth. So the Earth pulls on you with a certain amount of force. That's your weight. So when you stand on the Bethlehem scale, it actually has the weight on Earth. If you took the Bethlehem scale to the moon, it would be a different number. Your mass would stay the same, but your weight would change. So on Earth, we have an equation that uses Newton's second law. It says the weight of an object can be calculated by taking the mass of the object times a constant. This is the Earth constant, and the Earth constant is 9.8. So if you ever want to find, sorry, I'm blocking part of this, but if you ever want to find the weight of the object, this is the key thing to write down. The force of weight is the mass times this number, 9.8. This number is unique to Earth. So we say FW, the force of weight, equals the mass of the object times G, little g, and little g is 9.8. Okay, so we can calculate now. Again, we're using units. You're not familiar. If you're used to doing your weight in pounds, you stand on a Bethlehem scale, it gives you a weight in pounds. In physics, unfortunately, the United States is one of the few countries that doesn't use the metric system. So we would take your mass and multiply by 9.8, and we get your weight. Okay, and that will be in newtons. So mass never changes, but weight is a function of where you're standing. Even though on the Earth, it changes a little bit. And we'll do some examples later on. So let's do a quick example here. Calculate the weight of a person whose mass is 56. Well, this is obviously straight plug and chug. It's going to be FW equals mg. The mass is 56 kilograms. I'll talk about that in a second. And our constant for Earth, if you're on Earth, is 9.8. It's our acceleration due to gravity. That's what's pulling you down is gravity. So if I take that and multiply 56 times 9.8, it says my weight is about 548.8. 548.8. And that would be newtons. Again, unfortunately, we have a unit system that you're not used to because we live in the United States and we don't do what everybody else does. But it's a little unfortunate because it's not intuitive to you what this number means. If I said to you weigh 150 pounds, you'd say, oh, okay, that makes sense. Now, there is an approximation, and I don't recommend you ever use this, but I just want to give you a sense of what a reasonable number is. A kilogram. Now, kilogram is that chunk of metal that we used in some of the labs. When we did the inertia balance lab, it was a big, it's 1,000 grams. I think we did 900 in the pan at the very end. For 1,000 grams, it's about 2 pounds. So if you have a little gym and you have those little barbells, a little 2-pound barbell, that's about a kilogram. So you could just approximate. You could say, hey, you know, I weigh 220 pounds, so that means I'm about 100 kilograms. You could do an estimate. So if you can approximate that, but we're not going to use that. I tell you that so that when you're doing a problem, you calculate your mass to be 58 trillion kilograms. That's probably not a good number. Okay, so you don't need to know this fact, but it's kind of handy when you think about problems. So 56 kilograms times 2, it's about 130, 140 pounds. So that's a reasonable number for many of you. Okay. Now, let's do maybe 1 or 2 more quick examples. I apologize, this is a little tedious, but let's do a free body diagram. It has a car going down the road. There's a force from the engine pushing it forward, and there's air resistance and friction pushing it back. So again, I'll draw my car as a box. I'm going to say there's an engine, so the force due to the engine or applied is 1,000. And then we said that the friction and the air resistance together, so we'll put them together as one vector, we'll call this friction, is 725. So again, the free body diagram allows us to sort of get an idea of what's going on. Obviously, it's unbalanced. This is underneath there, it's asking which law it is, so it's obviously Newton's second law. And so they're not balanced. And now I can get now I'm going to use this to calculate some other stuff. So if I have the mass and I have the net force, well, I can calculate the net force. So it's going to be 1,000, so the F net, it's below anyway, but F net's going to be the FE minus FF. And again, I know you can do this in your head. 725, so that's going to be 275. So that's the net force. And again, I can set that equal to MA. So if the car has a mass, calculate the acceleration. So it's going to be F net equals MA. Let's extend this. What was the acceleration? So the acceleration is going to equal F net. Divided by M. We just said F net is the force of the engine minus the force of friction over M. 1,000 minus 725 all over 1,300. And so I can calculate the acceleration. Again, I can take the numbers and I'll plug them in the calculator. Okay, 1,000 minus 725. I know I did it above, and divided by 1,300. Now I'm going to get an acceleration of 0.21. It's a really tiny number, so it's not a very big acceleration, but you get the idea. Okay, it's just a number. All right, so you're going to use Newton's second law to find the acceleration. Now, as I said a minute ago, I could combine these with other things. This is one of my favorite slides. I found this on Google Slides, on Google Images, and I don't know what context this is, but it's kids tying ropes on rocks and dragging them. I really don't understand what this would be used for, but there's a little girl saying, let's play drag the rock across the table. It's the world's worst daycare. Now, if we say there's a applied force of 40 newtons applied to a 4 kilogram block, and the block accelerates from rest. So you can kind of see what's going on here now. We're going to combine Newton's second law along with kinematics. We're going to use the second law. In all the kinematic problems I did before, I always gave you the acceleration or we calculated it using kinematics, but now we're going to calculate acceleration using Newton's second law. So I have an applied force is applied to a 4 kilogram block, and it looks like that's the only force. So my free body diagram would look like this. I only have one force, and that's the applied force. It's it does say friction is pulling back the other way. So I can find my net force. So I'm going to say F net. And I do recommend, as we've seen before, setting the grid. So the F net's going to be the big one minus the little one. So it's going to be, in this case, it's FA minus FF. Kids always ask, is it always that? The answer is no. Every problem's unique. So you have to do every problem the same way, but you have to write the equation for each particular problem. So this kid's pulling on the rock, but friction's fighting it. It's not going to be balanced because they're different values. So it's going to accelerate. So I can calculate the acceleration by saying it's going to be the net force, which is FA minus FF over M. The applied force is 40. The frictional force is 25. And the mass of this rock is 4. So again, I'll do that calculation. It's going to be 15 divided by 4. It's going to be 3 point something, so it comes up to 3.75 meters per second squared. And the direction of the acceleration, again, is always in the direction of the net force. So the applied force when, so this thing's going to accelerate that way. They always point in the same direction. Now, we can now use kinematics, and I'll have to scroll here. It says, calculate the velocity of the block after 5.5 seconds if it starts from rest. So that sounds familiar. You can say VI equals 0. I know my acceleration is 3.75. I know the time is 5.5. And you're looking for VF. So it's straightforward kinematics, plug in numbers, get the value. So now we're going one step further. We're going to use the second law to get the A, and then use the A along with kinematics to solve something else. So again, we're sort of layering. We learned the kinematics, we learned the law, and then we put them together and use them together. And you can go ahead and calculate that. That would be equation 1. So it would just be VF equals VI plus AT. So A times T because VI goes out to 0. So we get 3.75 times 5.5, and I get 20.65. 20.63, and that would be meters per second. So you can calculate other stuff. I'm not going to do this. If you want to, this is Chapman, I think, for the Yankees. So it's bullets. And again, I'm trying to pick units that are that they're actually metrics. 45 meters per second is fast. And this guy can throw a good fastball. I think he's up around 100 miles per hour. So the pitcher wants to accelerate the ball from 0 to 45 in 1.1 seconds. That means while it's in his arm. So he's going to hold the ball here at rest, and he's going to accelerate it up to 45 meters per second in 1.1 seconds. So I want to kind of do this backwards. I'm going to say, let's take the kinematics, and then we'll calculate the force required. We'll do Newton's second law. So again, what I'm going to do is I'm going to set up a grid of keeping track of what goes where. The grid's really helpful for keeping track of things. So, well, the ball's going to accelerate from 0, so I know my VI is 0 to 45. I know my VF is 45. I'm going to have to do that in 1.1 seconds. So from that, I need to get A because I know the A is in Newton's second law. So I'm going to use equation 1 again. It's going to be VF minus VI over T. So it's going to be 45 divided by 1.1. I'll get a positive acceleration. So 45 divided by 1.1. So this is an acceleration of 40.9. Now this is why this guy makes a lot of money. Certainly more than me. He can make a ball go from 0. He can make a ball accelerate at almost 41 meters per second squared. I can't. I can make a ball accelerate at 1. This guy gets paid 40 times more than me. He probably gets paid 1,000 times more than me. But anyway, there's the acceleration. Now, calculate the force required. Well, I kind of lied to you here. I didn't tell you the mass. But I can calculate the force if I know the mass, because F net equals ma. So we're looking for the net force to cause that mass to accelerate. And I can't remember the number. I think it's 1.1 kilograms of the baseball. Somebody can look it up. But if I look up the mass of a baseball and multiply by the acceleration, I know how strong I have to be to make that happen. And I'm not anywhere near strong enough to make that happen. So 1.1. So if you can apply a force of 45 newtons to a baseball to make it accelerate in 1.1 seconds, you can be a multi-millionaire too. So all we're doing is we're using kinematics and Newton's second law, or in the previous example, we used the second law in kinematics. So we're kind of combining the two to solve more complex problems. And they get much more complex. I'm not going to go through it. There's an infinite number of these, but they're all kind of the same idea. Draw the free body diagram, look at the forces, look at the kinematics, just work your way through these. Now, again, a couple notes, and I apologize, I got called to this meeting last minute. I got an email the other day. It said, oh, by the way, you have to come to the meeting. So I didn't plan on not being here, but I'll pop in if I can break away from the meeting. I've assigned a Newton's second law homework. Don't take shortcuts. A lot of people just think I want the answer, but I don't. I want the steps. So it's not about the answer. Draw a free body diagram. Do everything algebraically. Make sure you're in proper units. In kinematics, we know velocity is mostly in meters per second. Acceleration is meters per second squared, or meters per second. Distance in meters, time in seconds. Mass has to be in kilograms. This is a weird thing about physics, the base unit is not a gram, it's a kilogram. And therefore the force will come out in newtons. So that's kind of the key. Apparently I wrote that again. So I'm going to assign the homework. I'll probably attach a Google form, so if you have trouble on it, I'll probably have to go over a couple of these in class. But I do want to get some grades in for you guys. So please have that done. Upload it as you normally do. I'll grade it, get a grade in there, but I will take questions. I suspect people have some questions, especially at the end. Okay? So I'll try and knock off there. If I can figure out how to turn this thing off. And then we should be good. Okay, talk to you later. Bye-bye.